Good evening. I'm Eric Walker, Chair of Highlands Astronomical Society, and it's my pleasure to welcome club members and new members who just joined recently, and also visitors from the north of Scotland sister astronomy clubs. Tonight is an all-club night. Tonight's timings are, I'll do the welcome. There won't be any notices because I'll be giving them in the club news section for tonight. We'll be having our main talk, which will be followed by questions and answers. And then we'll be doing the club news, Astropics and targets for the month. Some very good challenging targets for the month. At I don't know, 9:05, we'll probably be wrapping up, and that'll take us to the meeting close. There won't be any breaks during the meeting, so if you need to leave for any reason, just get up and go and keep yourself connected to the meeting. Now we're going to go straight into tonight, and I'm going to introduce our main speaker for tonight, who actually needs absolutely no introduction at all. It's our very own Pauline Macrae. We've got a good attendance tonight, and I'm sure that is on the back of Pauline's reputation for her extremely interesting and comprehensive talks. I'm setting you up here, Pauline.
I know.
Well,
Okay.
Pauline is going to give us an insight into Starbirth, and I'm going to hand over to her straight away. Pauline, it's over to you.
Thank you very much indeed, Eric. Okay, sharing my screen. Here we go. All right, good evening, everyone. What I'm going to try and do tonight is to answer 4 questions during the talk. Just going to move that little bit up there. There we go. So these questions are: where are stars born? How do we see them? How do stars form? And what are teenage stars like? Hopefully that'll give you a better understanding about the birth of stars. Well, star birth is beautiful and rather secretive, because baby stars are hidden in dense clouds of gas and dust. They're warm but feeble light, just not enough to penetrate the cocoons in which they're forming. We had to wait for ground-based telescopes and observatories in space that use longer wavelengths of light before we could see the development of these extraordinary nuclear furnaces that grace our skies. And although much more about the process is now understood, the details are still unknown, particularly for massive stars. So hydrogen and helium gas pervades the universe in proportions roughly 75% and 25%. And these are the most abundant gases in the universe. Why should that be? Well, it's because of the Big Bang, and these elements were the first to appear. So the hydrogen fuel was already present for stars to form and burn. Okay, so our first question is, where are stars born? Well, if you've ever looked up at the Milky Way, you'll see a wondrous carpet of stars stretching from horizon to horizon across the night sky. And if you look carefully, you can see dark patches within. And these are dark clouds. There we go. Which consist of gas and dust. And it's the dust that obscures the stars beyond. Now, red light can penetrate the dust more easily than blue light. So the clouds appear more transparent at longer wavelengths. And when viewed in the near infrared, which is what we're doing here, then apart from the very thick areas of cloud, of dust, the cloud just seems to disappear. And many of these dark clouds are associated with H2 regions. There we go, these are the red bits here. They're also known as emission nebulae, and they're found in or close to the Milky Way. And these tend to look red in long exposure photographs, but our eyes don't see color at night. So H2 regions will not look red through a telescope. H2 regions are areas with one or more large, very bright and very hot stars, emitting ultraviolet light that heats up and ionizes the hydrogen that's present. And this means that the ultraviolet radiation produces enough energy to snatch away the electron and from the hydrogen atom, but an electron, because there are plenty of electrons around, an electron can rejoin the hydrogen atom. And when this happens, light is released at a characteristic wavelength and the area glows red. And that's the simplified version, as there is a little bit more to it than that. But there's a lot of hydrogen and it doesn't take much to ionize it. So that's why these areas appear predominantly red. Now, H2 regions are linked with starbirth and usually mark areas where new and massive stars have already formed. And they are the ones that provide the most stunning of images. They tend to be found in the spiral arms of spiral galaxies, including our own, because this is where we find the clouds of gas and dust, and they mark the spiral arms. And okay, the Whirlpool galaxy has a few more H2 regions than our galaxy, but that's because it's had a close encounter with the smaller galaxy here. So the gas within these clouds mostly consists of hydrogen molecules, and these form under very cold conditions. And there are, of course, a sprinkling of other molecules, hence the name molecular clouds. Now, one of those molecules is carbon monoxide, and this can act as a tracer of molecular hydrogen, which is itself extremely difficult to detect. So this is the carbon monoxide within our galaxy, or within the disk of our galaxy here. So by mapping the radiation of carbon monoxide, it was discovered that these molecular clouds are huge and concentrated within the spiral arm of the Milky Way, which of course is also where we find the H2 regions. So this image is of the entire sky in mid-infrared wavelengths, and it is showing the warm dust that is present in our Milky Way, and that's what the bright stripe is, extending from left to right, showing up the warm dust in the disk of our galaxy. And then we've got various bright regions, these little white patches, as well as the redder areas of the sky, and these correspond to strong infrared radiation, indicating the sites of newly born stars. So if we flick back and forth between the infrared and carbon monoxide images, you can see how well the carbon monoxide traces the molecular hydrogen. So there's Taurus, which you can see. This is the Ophiuchus clouds. Oh, sorry, wrong way. There we go. Large Magellanic Cloud, and of course, the Orion region, which is over here. And really, you can see that the carbon monoxide molecules can trace the molecular hydrogen and the dust in some of these very well-known starbirth areas. But the brightest region in the very center of this image is the center of our galaxy. And we're not seeing newly formed stars here. We're seeing old stars that are crowding together. And these are red giants and red supergiants, and they produce a lot of dust in their old age. And that's what the infrared light is picking up here. So the very largest of the molecular clouds are the giant molecular clouds. And these form the bulk of star formation, as they contain most of the molecular hydrogen. They can be gigantic, up to 600 light years in diameter, containing perhaps 10 million solar masses, which is an enormous amount. And if you look at the average density of atoms in space, you'll find 1 particle per cubic centimeter, whereas the average density of a giant molecular cloud is 100 to 1,000 times as great. Okay, it still wouldn't be enough for us to breathe, even if we changed all the hydrogen molecules for oxygen and nitrogen. But when you think about space, it's an awful lot of molecules. And this image here shows Orion, which is our closest giant molecular cloud at about 1,300 to 1,500 light years away. Now, there are smaller clouds which are closer still. And the Taurus and Ophiuchus clouds are only 300 to 400 light years away. Now, these intermediate clouds contain perhaps thousands of solar masses, down to hundreds of solar masses, even all the way down to 10 solar masses. So there's quite a wide amount of solar masses within these clouds. The Ophiuchus complex itself is presently forming around 100 low mass stars. And that makes sense. Small cloud, fewer stars. And of course, they're more likely to be low mass stars because it's a smaller cloud rather than massive stars. And then at the far end of the scale, there are Bok globules, which are only about 1 light year in diameter. So you can see that this Bok globule is the same as this one here. But in this photograph, we can see all the bright, massive stars that are gradually wearing away the cloud in these areas. And these Bok globules are very often compact, they're very dark, and commonly found within H2 regions. And I'll come back to that at the end, very close to the end of the talk. So, next question, how do we see what's going on in these clouds? How do we see stars forming when they cannot be seen in visible light? Well, I've already given you a few clues. Basically, we need to use longer wavelengths of light. Now, baby stars, especially at the earliest of stages, are cold objects. And the colder an object is, the longer the wavelengths of light that it emits. And these include cold dust. And a lot of the radiation we see comes from cold dust. So observing the sky in long wavelengths, particularly sub-millimeter wavelengths, allows astronomers to look at some of the coldest sources in the universe. And here you can see some of the temperatures picked up by sub-millimeter wavelengths. So this is 3 Kelvin. That's 3 degrees above absolute zero. It's minus 270 degrees centigrade, all the way up to around 30 Kelvin. So these are picking up extremely cold sources. And this would be the infrared area of the sky, and this is our visible wavelengths. And if we divide the infrared region up, we usually get something like near infrared, mid-infrared, don't usually come across thermal, but there we go, that's part of the mid-infrared. And then we have the far infrared, which actually is usually split into far and the sub-millimeter wavelengths, because once you get to 1,000 microns, that's the same as 1 millimeter. So in this image, we've got Orion in visible wavelengths, but as soon, or I should say this is the Orion Nebula, just to try and orientate you, but as soon as we use sub-millimeter wavelengths, we see this orange glow due to dust that is perhaps just 10 degrees above absolute zero. And it shows us when new stars are forming. This gives you some sort of context as to where these dusty areas are. And you can see that this region matches that orange glow really quite nicely. M78 is another area of Orion that they have been studying very carefully in these sub-millimeter wavelengths. And it shows how important they are, because you can see that there's really nothing in these circles here or in these. That little tiny star in there is most likely a background star. But as soon as you use sub-millimeter wavelengths, now you have got these extremely young stars. And then mid and far wavelengths gives you these other colors. But that just simply indicates how important sub-millimeter wavelengths have been. So starbirth takes place in dense molecular clouds, which we see as dark clouds, as you can see here. Or if starbirth has already started, then we also see the beautiful colors of these magnificent areas as gas is ionized. So our third question, and this is the one that this is the longest section. How do stars form? Well, molecular clouds are really complex, particularly giant molecular clouds, and they often contain filaments and sheets and bubbles and irregular clumps. Now, filaments appear to be particularly important for star formation because they are found in all molecular clouds, and they consist of a lot of dust which may form after strong turbulence within the cloud, maybe pushing some of these dusty, thick, denser areas together. And it seems that the biggest filaments draw in material from a smaller network of filaments, rather like capillaries draining into veins. And then the densest parts of the filaments will form clumps with dense cores. And this is another filament, which is this time in blue, and that picks out the coldest part of the cloud, coldest and densest part of the cloud. So we are looking at dust of minus 259 degrees centigrade. That's just 14 degrees above absolute zero. But if you have a look at these bright spots here, these are the seeds of future stars. Now, I might have mentioned how cold these molecular clouds are, but they have to be very cold before gravitational collapse can occur. Too warm, then these molecules have too much energy. They're zipping around all over the place. Gas pressure is high, and they'll keep gas apart. Whereas when the molecules are cold, then they're able to get very much closer. This increases the density and increases gravity, which then can take over. In effect, gravity wins against gas pressure, and the collapse of a cloud core can begin. So once again, we have filaments within this blue-colored cloud. This is very, very cold and dense, but the pink areas where we have the filaments, well, they're even denser. And they're also slightly warmer because things are happening in these filaments. And what they have found, which is really interesting, is this bit here called LINS 1544, but it is a cold pre-stellar core. And it has been found to have water vapors surrounding it. And observations show that the water molecules are flowing towards the heart of the cloud. And that's what this velocity is all about. It just shows the movement of these water molecules. And that suggests it's already collapsing under gravity, even though there's no sign of any forming star. It's simply a cold core, but it's the first indication that star formation has begun. Now, as this core continues to contract, the cocoon of the infalling gas and dust becomes so dense and opaque that it begins to trap any radiation released by the stellar embryo, which is that little tiny dot in the middle there. And it will be slightly warm. It will be producing a tiny amount of light, but it won't shine itself. What it does is to actually warm the cocoon, which then re-radiates the heat, the energy in the form of heat. And at this very early stage, only observations with sub-millimeter wavelengths can detect its presence. And that is what we are seeing here in the Taurus molecular cloud. And each bright point is a stellar embryo surrounded by its cloud of gas and dust, although we are not actually seeing the stellar embryo, but the heat from the cocoon that's surrounding it. Now, the embryo can have a mass that is 1/100th of the mass of our sun, but a diameter that is out to the radius of Jupiter. So it's big and it's fluffy, but still small relative to its birth cloud. And over the next tens of thousands of years or so, it gets smaller as it continues to contract, and it grows steadily denser, and the core temperature rises. The outside doesn't rise an awful lot, but the core temperature does. Eventually, it'll reach something like 2000 Kelvin, and then it's called a protostar. So the process of collapse creates a lot of turbulent motion, which results in the rotation of the cloud and forming star, giving it a problem, because the gas and dust from the surrounding cloud can't land on the baby star very easily. I mean, stuff is falling in from all over the cocoon, but the star is rotating more and more quickly. And the result is that the gas and dust form a flattened, rotating and extended disk around the equator, so that material can now flow from this onto the protostar. And what we are seeing in the Orion molecular cloud are the disks of the baby stars. So the yellow dots are the locations of the forming stars, and each square contains images of them made by ALMA and the VLA. Now, ALMA is the Atacama Large Millimeter and Submillimeter Array, and you'll see it down here or acknowledged quite a few times. The VLA is the Very Large Ray, which goes into millimeter wavelengths. So the ALMA images show us the outer part of the disk, and the VLA show us the inner part of the disk and the stellar embryo. Although remember, it's the heated cocoon that we are actually seeing. Now, this enabled astronomers to get an idea of the size and the mass of the disk overall. And this disk can be absolutely enormous, sometimes around 500 astronomical units, and I have seen 1,000 astronomical units quoted. So 1 astronomical unit is the distance between the Earth and the Sun. 40 astronomical units is the average distance between Pluto and the Sun. 1,000 astronomical units is the distance between the outer edge of the Kuiper belt and the Sun. And of course, remember, this won't be to scale. So these are really large disks. And research has found that the younger the disks, the more mass they contain, which makes sense because that disk is feeding the protostar. So as the protostar gets older, the mass of the disk will reduce. So the disks you can see here are around extremely young stars, although we're not seeing the actual disk, but the heated dust in the clouds surrounding the baby star. And as collapse continues, the forming star rotates faster to conserve something called angular momentum. And angular momentum turns out to be rather important when it comes to making a star. And we can think of it as the amount of rotation in the forming star. And just like an ice skater who, when pulls in their arms, increases their spin, so the contraction of a baby star will result in a faster spin. This generates another problem, because if it carries on like this, contracting and spinning ever faster, the baby star will end up by tearing itself apart. So it has to reduce its angular momentum somehow. And one of the things a baby star can do is to form a disk. And as you've seen, it does that early on. Eventually, though, even the disk has to reduce angular momentum. Otherwise, it'll rotate so fast that the baby star cannot feed from the disk. And that's because the protostar and the disk are coupled by magnetic fields. And it's now thought that the disks form spiral arms, which can transport material both inwards to accrete onto the forming star. And this looks very much as though this is part of the accretion point, but there was nothing in the information I read to actually confirm that. But the other thing is, it can also, these spiral arms can also expand the outer disk and helping to transfer angular momentum away from the inner disk. That then slows the inner disk down and it allows the protostar to feed. So bear with me on this one. At the same time, the magnetic field is pulled inwards by the contracting star and then protostar, sorry, cloud. And it takes on the shape of an hourglass. And then something amazing happens. Interactions between the magnetic fields of the protostar and the disk somehow changes the direction of some of the gas and dust that's moving towards the protostar and away from the disk. And then it ejects it from the magnetic poles of the baby star, funneled by the hourglass shape of its magnetic field and by the surrounding disk. And this is what we observe as jets and bipolar outflows. Now, these are real images of protostars. And what they've also been able to do is to map them in different stages to see the beginnings and the progression of the bipolar outflows. And then that's the artist's impression as to what is going on. So here we have an actual disk with this bipolar outflow. And the disks are rotating, which means that the outflows also must be rotating. And the magnetic fields most likely help to launch the outflows and to keep them collimated. Now, this has been something that's been assumed for a long time, that everything is rotating. But it's only over the last few years it's actually been confirmed. This gives you an idea of scale. So it has reduced a bit, but it's still enormous compared to our the orbit between, for instance, Neptune and the Sun. And what the jet seems to do is to take material from the inner part of the disk and then blast it outwards like bullets, carrying away most of the angular momentum, slowing the spin of the accretion disk and allowing material to transfer from the disk across to the protostar so it can feed. But notice that feeding is not onto the equatorial regions of the star, which is what we might expect. And it probably started off this way, but instead, and don't worry about this diagram, I just want to see if I can make it a little bit clearer, because what happens is that gas is funneled from the disk to the polar regions of the star via bridges made by the magnetic field. How amazing is that? And it seems that the bipolar outflows are one of nature's ways of solving the problem how to build a star from material with angular momentum. So what we're looking at here is an outflow and jet from one of the youngest baby stars known at just 10,000 years old. Now, we can't see this in visible light because it's hidden within the cloud. So this is infrared light. The star is here, or behind, or within, I should say, the disk, which itself is in shadow. And then the star is lighting up these parts of the gas here. And this star is only about 5% the mass of our sun, so it's still accreting. And we can see pulses within the jets at fairly regularly spaced intervals as the baby star gulps down its food. And then near the ends, we've got these large bow shocks, which spread out into space as they collide with the surrounding cloud. So we're now looking at the previous outflow, and that was that pointy bit. We're just in a different orientation. I love the way astronomers can dissect these outflows and their disks to understand what's happening. So what we're doing really is gradually zooming in on various parts of the outflow, the jets and the disks. So here now we are looking at the central part where we've got the beginnings of the jet and the disk. The colors and what we're able to see is represented by different molecules that are actually looked at. But I'm not going to explain all of that. And finally, we have a close-up of these jets and the disk. And from this, they were able to determine that the disk is definitely rotating. And from that, they were able to confirm that the jets are also rotating. So these outflows are quite extraordinary, and they're thought to be produced by all forming stars, starting very early on in their formation. But they can't always be seen. Now, we can see these jets, okay, but the protostar itself would be hidden in this cloud of gas and dust. Whereas here, if we look in the visible image, we've got the jet, which you can see here, but you can't see the other side of it because it's buried along with the protostar in this dense cloud of gas and dust. Sometimes all we see are these strange lumpy nebulae, and when their paths are traced backwards, they lead to very young stars buried in the dark clouds where they've been born. So this is a jet called HH4647. Have a look at how long this jet is, 4.8 trillion kilometers. These are absolutely huge. So the baby star, as I've said, is hidden in this Bok globule here. But if you use sub-millimeter wavelengths, you can see the other end of this bipolar outflow. And this, of course, is overlaid onto the visible wavelengths. If we use infrared light, you can now see the disk in shadow, and you've got beginnings of a jet on the other side. So the protostar would be in here within that dark, dusty disk. And sometimes these outflows are found in pairs on either side of a protostar, which may still be buried in its birth cloud. So in here. And these outflows are in the form of ionized gas. And that's because they move at speeds of several hundreds of kilometers a second, so that when they collide with the surrounding gas and dust, the resulting shock waves generate visible light, giving rise to the jets, sometimes the outflows, and very often these patches of bright emission, which are called Herbig-Haro objects, after the first two astronomers that described them. But any part of the outflow, whether it's a jet, the bipolar outflow, all these nebulae are known as Herbig-Haro objects. And that's why, if you've noticed, they're all called HH and followed by a number. And careful observations show that they change over just a few years. So this is 1994, all the way to 2007. And the first thing you notice is that they've moved in that short period of time. That's because they're moving so fast. And then you find that there are existing knots of emission which become brighter or maybe fainter. Perhaps they disappear completely. Or maybe new knots are forming when nothing was previously detected. And that fits in with the material being shot out of the polar regions like bullets, perhaps indicative of the way that protostars feed. And the larger they are, the more powerful the jets. It's very likely that stars of all masses form in this manner by collapsing under gravity, accreting material, producing disks and bipolar outflows and jets. The main distinction is mostly in the time it takes for a star to form. Now, the very lowest mass stars may take over 100 million years to reach maturity, whereas it might be just 100,000 years for the highest mass stars. Our sun would have taken maybe 30 to 50 million years to become a fully fledged star. It depends on which books or which websites you happen to read. So how do young stars behave when they become teenagers? Well, that depends on their starting mass. So what we're going to do is to have a look at low mass stars first. So this is a Hertzsprung-Russell diagram. This is temperature, cool, hot. This is brightness, dim, bright. So if we have a look at classes F, G, K, and M first, and our sun is in G class. Now these stars are cooler, smaller, and they are less bright. Remember, they're down here, so they're going to be less bright, and they are cooler because they're in the red side of things. And to be on the main sequence, which is what this is, you have to be a grown-up star, a mature star. They have to be burning hydrogen into helium. And at the point where the protostar has gained more than half its final mass, has used up a lot of the material in its disk, and its jets and strong stellar winds are starting to blow away the surrounding cocoon of gas and dust so that it becomes visible, it's known as a pre-main sequence star. Pre, because these stars have not yet reached the main sequence. And remember, stars can only be on the main sequence when they are burning hydrogen into helium. So these low mass stars, low mass pre-main sequence stars, are called T Tauri stars, named after the first of its kind discovered in Taurus. And here is the original T Tauri star, which actually turns out to be 3 stars. So it's now considered not to be an ideal T Tauri star. And also notice it's beside a nebula, and you've got this cloud around about it. So this is Himes variable nebula. Now, these T Tauri stars tend to be associated with dark or bright nebulae. And we now know that this is because they were born in these areas. And the Taurus Auriga dark cloud is a known hotbed of such stars. And look at the jet that we've got here and the disk. And then if you look at this one, XZ Tauri, I'll come back to that in a little while. So T Tauri stars are under 10 million years old, and they have a number of characteristics which distinguishes them from fully fledged stars because they look like proper stars until you examine them really carefully. And the first is that they vary irregularly in brightness. So they are variable stars. And there are a number of reasons for this. They have huge dark star spots, which may increase and decrease the light as the T Tauri star rotates. They can also produce brilliant flares, and this is that XZ Tauri that I pointed out. You can see how big this flare is, and you can see it's also a binary star. And this can create dramatic increases in brightness. But the other explanation of their variability is due to the way they feed. It seems that large lumps of material from the disk can slam into the protostar, locally heating the gas to extremely high temperatures and leading to a spectacular increase in brightness. And McNeil's Nebula is a good example of this. In 2006, the nebula was barely visible. In 2008, it had brightened considerably. And that is the protostar there. This is a really nice photograph of it. Perhaps it had ingested a lump of material or two, and it's possible that all forming stars may feed in this irregular fashion. Yet, while feeding, they can also be building planets, and their dusty protoplanetary disks make them very noticeable in infrared wavelengths. Remember, dust shines in infrared wavelengths. Now, our sun probably had a disk very similar to this that then gave rise to our planets. So, I mean, this is a real disk, and you've got the gaps within it where planets are forming. But look at this. This, they think, is a real planet, a Jupiter-sized planet. Absolutely extraordinary. They also have distinct spectra with this bright line of hydrogen alpha, which may have something to do with their jets. But what's important is this. This is an absorption feature of lithium. And lithium is destroyed by nuclear fusion in main sequence stars. But remember, T-Tauri stars are just teenagers. They haven't yet started hydrogen burning, so lithium is a sign of their youth. Now, while T-Tauri stars have their disks, they will maintain their outflows. And we're not seeing an outflow here because they're not using the correct wavelengths of light to pick it up. But without their birth cloud to fuel the disks, both disks and outflows will weaken and disappear, resulting in much reduced infrared emission because there are no disks, and only weak hydrogen alpha emission because there are no jets. And then over the next tens of millions of years, depending on their starting mass, T-Tauri stars continue to contract, but very slowly. So they can be plotted onto an HR diagram, Hertzsprung-Russell diagram, but they tend to be plotted separately to show how their temperatures and luminosities change as they slowly mature. This is where they're heading, the main sequence. And so they're starting around here. And you can see that they are bright because they're right up here in the luminosity, in the high end of the luminosity scale. But they are also extremely big, which is why they're so bright. And this is 100 times the radius of our sun. And as they slowly contract, they get smaller. You see, we're heading for the 10 times the radius of our sun. And because they're getting smaller, they're getting dimmer. But they also get denser until core temperatures start to rise. The outside temperature, not a great deal, but the core temperatures now at this point begin to rise because things are happening inside the T-Tauri star. And eventually the core will reach a critical temperature of around 10 million degrees centigrade when the nuclear fusion of hydrogen into helium begins. And at that point, we have a fully fledged star, and it can be found on the main sequence. What about pre-main sequence stars that are between 2 and 8 solar masses? Well, these are the analogues of T-Tauri stars, but they're called Herbig AE-BE stars because their spectral types are A and B. Therefore, they are much hotter, this is the hot end, and they are also much brighter than their low mass counterparts. The E stands for emission, the AE-BE bit, because they also have bright hydrogen alpha emission lines like T-Tauri stars. But since they accrete material much faster, much more directly than T-Tauri stars, it only takes them 5 to 10 million years to become a mature star. So they miss their early teenage years going straight to their late teens. And they're often found with T Tauri stars within the same molecular cloud, because that's where they were all born. And they are very bright in the infrared. So this star here is the same as this one in infrared. So you can see that very easy, it outshines all the other stars in the image. Hopefully, you will find that by the time they've lost their disks and their outflows, they will have formed planets. And that is what's happening here. So this one obviously still has its disk. And what they reckon is this little bit here, that could be where a planet is forming. And then shortly after that, they should join the main sequence. So finally, we have the most massive stars, that is, those greater than 8 solar masses. So we're looking at the high end of the B stars and the O stars. So they are up here, except they've not actually drawn any dots where the O stars should be. But these are the really big stars. But finding the precursors of these behemoths is incredibly difficult, because not only are they rare, perhaps just 1% of the total stellar population, but also because they evolved so quickly in around 100,000 years, compared to millions of years like our sun. And this means that when they become fully fledged stars, they are still enshrouded in their birth cloud. And that means they never become teenagers. It's like they were born adults. So seeing how they evolve is extremely difficult and is an area of ongoing research. So they will form from the largest cores in the largest molecular clouds. But the question is, do they undergo gravitational collapse like lower mass stars, or do they form by cannibalization, as some astronomers think? So this rare glimpse into the early life of a massive protostar shows a huge amount of material, of cold gas and dust here in red, that is flowing into a central compact region, which you can see here in yellow. And this supports the theory that massive stars do indeed collapse in the same way as lower mass stars. And then another question involves their growth. So it's thought that they start cool and fluffy like lower mass stars, but because of their size, they heat up really quickly, which means that they can only accrete up to a certain size before radiation or gas pressure increases so much that the gas in the cloud surrounding the baby star is pushed away, forming an opaque cavity. At that point, especially if, as long as there are no outflows, the gas and dust or radiation can't escape, and the gas and dust is prevented from falling onto the protostar or its disk, and its growth is stopped. In addition, massive protostars will launch strong bipolar outflows, which can eject so much material that it reduces the amount available to accrete. Now, these images here, which have been translated into this artist's impression, thank goodness, were taken just 16 years apart, and they show how quickly the outflows can get going. So these problems suggest that massive stars shouldn't exist. So how do they gather enough material to become the sizes that they do? Well, radiation or gas pressure should reduce once the jets blast holes in the cocoon, as you can see here, and that allows some of this radiation to escape. And that means that material can then continue falling in. And just as with McNeil's nebula, there will sometimes be large blobs that may fall onto the disk or straight onto the protostar, causing an extreme hotspot at the impact site. And this can cause a dramatic brightening. So in this image, the protostar is not visible. But after the outburst, it became the brightest infrared source in the entire cluster. And here's another outburst, again, most likely due to the way massive stars are gulping down these huge mouthfuls of material. And it's now thought this could be an important way that massive stars manage to accrete the amount of mass they need, but may also be a way all stars ingest material. So massive stars are extremely hot and begin emitting ultraviolet light even before they are fully mature. And this can have a big effect on their environment and therefore on the lower mass stars around them, because it's the massive stars that are born first. Despite their radiation, strong winds and outflows, they are still fighting with their birth cloud when they reach the main sequence. The ultraviolet radiation that they produces these hot bubbles of ionized gas that begins the formation of H2 regions. Gradually, these bubbles expand and produce shock waves as they plunge into cold gas, which is then compressed, and the gas is slowly ionized, enlarging the H2 region. And the bubbles can expand easily into low density areas of gas, but are stopped when encountering higher density regions full of dust. And only gradually does the radiation and the fierce stellar winds from the hot young stars erode the thick dust, carving pillars which point to the massive stars. So basically, they are pointing to their destroyers. Ultraviolet light slowly eats into the edges of several clumps, eventually eroding the cloud away until all that's left are isolated Bock globules, which is why you'll often find them in H2 regions. Now, these massive stars produce so much ultraviolet light that if a protoplanetary disk is too close, it will be exterminated. The protoplanetary disks seen by Hubble show that many have these teardrop shapes, and with the dust and gas trailing away from a nearby massive star, which will be found here and here and here. And the disk will slowly evaporate. But with enough distance, the disks will hopefully last long enough to allow the formation of planets. So this looks like a more normal disk, whereas here we have a teardrop shape, and look at where it is, right where the trapezium is. So it's facing probably the most massive of the trapezium stars in Orion. Now, over millions of years, these ionized bubbles, and you can see bubbles blown within the Orion Nebula. There's a big one behind the trapezium stars, apparently. And these bubbles can sweep through the cloud, disrupting and destroying a large proportion of it and preventing more starbirth. And if that's not enough, massive stars die young, exploding as supernovae, flinging their contents into interstellar space to mingle with molecular clouds, leading to yet more destruction. But then the compressed gas cools down, loses its ionization, and it can become dense enough to form more stars. And so the great cycle of starbirth begins again. What an extraordinary journey stars travel to go from these enormous clouds of gas and dust only a few degrees above zero, collapse, become denser and hotter, develop disks and bipolar outflows to eventually become a much smaller, relative to its birth cloud, and much hotter star with core temperatures of many millions of degrees centigrade, generating energy by nuclear fusion. a fully fledged star. Now, while stars are not quite like the miracle of life, like my 4th grandchild born just 2 weeks ago, they are nevertheless also one of nature's wonders in this astonishing universe of ours. Thank you.
Oh, Pauline, that is superb. Well, I feel like my old exam days where I've just revised and I think I could do a good job of answering the question tomorrow. Give me a week, not so good, and a month I'm going to have to be revising again. That's superb.
Thank you very much, Harry.
Yeah, a few questions coming in, a couple from me as well. See when you're studying something like this or observing something like this, during the early stages, the embryo stage, the cocoon stage, I can see you would need to have a range of infrared detectors to detect, the change in warming temperatures. Otherwise, it could look like at a certain stage the thing was disappearing. So you'd have to have a sort of structured set of IR detectors or variable wavelength detectors. If I've read this right.
Yeah, I believe you do. You've got these ground-based telescopes, and you've got the infrared space observatories, and they have a range of infrared wavelengths starting at the sub-millimeter end, with sometimes a little bit of millimeter wavelengths, all the way through to this far infrared, mid-infrared, and near infrared. It's the near infrared that makes the dust disappear, but the mid-infrared is able to pick up dust. And then as you get colder, you begin to see these colder and colder sources. And generally it is the dust that is being picked up by these detectors, but the colder the source, the longer the wavelengths. And that seems to be how it works. So by using lots of, or the wavelengths of infrared light all the way through, or these longer wavelengths of light all the way through from one end to the other, you can then pick up a range of temperatures so that you can see these stars in their different stages. And I didn't mention it, but of course the James Webb telescope, as long as everything works as it should pick up these stars in even earlier stages. And that is one of the things that it will be doing. And this is something that astronomers are looking forward to, because not only can it pick up really cold sources, but it has a much higher resolution because of its 6.5 meter mirror. And that is also extremely important. So it's a resolution to be able to see these tiny things, and maybe it'll be able to pick up more than just the heat from the cocoons. But I mean, what they are managing to see is just incredible. And I love all these jets that you can see. And there was another image that I didn't show you, but it was full of protostars and lots of little tiny green things. And those green things were all these bipolar outflows. But again, it was in a different wavelength of light, and different wavelengths of light will give you different colors. And it was just extraordinary. So yeah, it's amazing.
Yeah, well, you've just taken two of my questions off me, the James Webb one. But it's like, but you've answered them perfectly, because I was going, what I see, it's a wide range of infrared detection, wavelength detection it's working on. But the higher resolution could be something quite spectacular, actually. I mean, remember when Hubble first brought back these high resolution pictures, and we were all just jaw-dropping stuff. So I really am looking forward to that.
Yeah, no, it should be good.
Yeah. Right, we've got a few question and answers now from Colin. Hi, Pauline. Do all the sun rotating gas disks, do they all move anti-clockwise?
You mean are these the discs?
I think when getting rid of the discs, getting rid of the angular momentum.
Or just the cloud?
Yeah, I think so. Yeah.
It depends on which way the cloud. I mean, all clouds will have a little bit of movement because of all this turbulence that's going on within them. So it may be that there will be some that will rotate the other way, but I think a lot of rotation is relative anyway in space. And although, I mean, when you look at a lot of galaxies, they seem to move in an anti-clockwise direction. So I think a lot of things tend to move in an anti-clockwise direction, but I don't know for certain. But that seems to be the direction that everyone gives. I mean, certainly our solar system and everything in it works in an anti-clockwise direction.
That's a fair answer. I just think you've just made me think it depends where you are, because if you're on the other side, it's going to move clockwise, isn't it? So yeah.
It's all relative in space.
We're going to go down a rabbit hole here.
I can imagine.
Here's one from Mark Brain, and it's he's asked, how do binary stars form? And I want to expand that as to how do multiple star systems form? You know, is it the same way?
Yeah, what I've done is to concentrate on one star, because as soon as you start bringing in other stars, it gets a lot more complicated. I mean, they have all these wonderful computer simulations where they show multiple stars forming, and that is the norm. You won't, or you would very rarely get stars forming singularly. Even Bok globules, which are only about a light year in diameter, they will form possibly a binary, maybe a triple star. So most stars that are formed will be in groups, in clusters. And of course, in clusters, you'll get a range of stars from the very massive stars through the intermediate, those are the big AEBE stars, down to the low mass stars. And of course, you get far more low mass stars formed than any of the higher mass stars. So yeah, and they are formed in the same way. There are certainly some stars that will cannibalize each other. Now I took the picture out because of time constraints, but there's a wonderful image of what looks like fireworks within the Orion Nebula, and that is thought to be due to massive protostars possibly colliding and produce this huge explosion. So it's not just supernovae that produce explosions, but this also did. So that can happen because although these stars are never that close, because their disks are so enormous, they actually can interact, and therefore they can end up by being flung out of the system or being merged together. But the other thing about this angular momentum is that you won't always just form a disk. Sometimes the whole star will split. Sometimes you'll get a lot of splits. So you end up with lots and lots of stars being formed. So probably the best thing to do is to look at one of these computer simulations of all these stars forming, and you can see it in that way. But yeah, all stars are formed in clusters of some sort.
Yeah, as you were giving your talk there, you see, I was starting to get a grasp of it. I was going, yeah, there's not just one star forming in that area. So, you know, it's like an explosion of, I mean, it's not an explosion, but it's like an explosion, and one's bound to impact on the other and change its dynamics and all kinds of things. Got a question. Sorry, question.
No, I'm just going to say this. This is the thing about the formation of the stars, because with the massive stars forming first, as I said, you'll get all this ultraviolet light really changing the environment. But not just that, as soon as any of the stars start forming and they produce these jets and bipolar outflows, you're changing everything within that environment. And stars are going to end up by not getting the gas and dust that they need, and it'll disappear and they'll be moved away. So there's always something happening in these areas.
Yeah, Patricia Burton's asked, it's going on with the rotation. Does the anti-clockwise or clockwise rotation of the gas, does it have a cause or a reason?
For the rotation?
Yeah.
That's turbulence. Apparently, these clouds are full of movement. But again, you know, if there's anything happening within these clouds, if there are supernova explosions a long way away, for example, that shock wave will impact on the cloud. If there are other stars that have been formed, again, they're going to push the gas away and again impact any clouds that are there. And all this turbulence can then start rotation. Magnetic fields are supposed to have a big part in this. And I could have put in more about
magnetic
fields,
I know you can.
I thought not a good idea.
As Stephen Chapman's asking, what's this dust made of? It's nothing like it's on my top shelf.
Well, it seems to be millimeter size particles of silicon and other grains of stuff that you get in supernova explosions. It's this, and you would have various elements that would come together if it was cooler, if it was cold enough, and those elements can then form solid particles. But we're talking about really tiny particles. But of course, this is what you get with supernova explosions, seeding the molecular cloud. So it's not just gas they produce, but they also produce a lot of these particles that can form dust in the end.
Ah, cool. Right. Well, Pauline, I think that's it. You're off the hook now. That was just wonderful. Really was good. And
thank you.
Everyone's just enthralled. I was concerned there was no questions coming in, and they all came in at the end. That's fine.
That's brilliant.
But absolutely wonderful yet again.
Thank you.
I'm going to hand over to you now.
Absolutely. Right, because now I would like to introduce our very own Eric Walker, our chairman, who is going to do the Club News and Astropics. So away you go, Eric.
Okay, I'll just work out how to share the screen. Is anyone tell me if that's shown okay?
Yeah, that's fine.
Okay, cool. Well, welcome. I'm about to do Pauline's bit, so I'm the apprentice, so I'm sure I'll get the feedback after it. And tonight we're going to talk about Gemini. Gemini, in Greek mythology, it's associated with the myth of Castor and Pollux. Now, in Greek mythology, these guys weren't twins. Pollux is the son of Zeus, and he is immortal, whereas Castor is the son of Tyndareus, who's the king of Sparta, and he is immortal. And when Castor died, Pollux begged Zeus to give Castor immortality, which he did by uniting them in the heavens forever. Now, this is a stellarium schematic of what's in the night sky pretty much about now. Actually, this is set for tonight at 9 o'clock, and you can see all the big what I call the big constellations, the big winter constellations are there in the southern part of the sky for us. Pauline talked about Canis Minor last week, and here is Gemini just up to the top left of it as we look. So it's really, really well placed at the moment for looking at it and then examining it and studying it. Pauline referred to the asterism, the Winter Triangle, last week, which is part of an even bigger asterism called the Winter Hexagon. It's very easy to spot. I mean, the stars that form this asterism, or the stars your eyes are drawn to, are extremely bright. You will easily see Capella in Auriga, Aldebaran in Taurus, Rigel in Orion, the dog star Sirius, which Pauline talked about last week, Procyon, the little dog, and Pollux, which is part of the twins. So it's very, very easy to locate. Gemini is easy to locate. I usually use Rigel, go through the belt stars up to Betelgeuse, and I just extend it, and that's me up to Gemini. That's the easy way that I tend to find it. Here's a big diagram to show you the alignment of all the stars, and I'm going to go into this in a little bit more detail. There's Castor, that's Alpha Geminorum, Pollux is Beta, and I'm going to look at gamma as well. Now, this is the diagram I'm going to refer to. It looks a bit messy, but bear with me. This will help you find the features that I'm going to talk about. And the first feature I want to talk about and encourage you to look for are the main stars of Gemini themselves, Castor and Pollux. Now, Castor and Pollux. Pollux is in actual fact the brighter of the two, although it's beta Geminorum. It is the brighter of the two. It's about magnitude 1.2, I think it is, 1.16, something like that. And it is a red giant. So it's going to the diagram that Pauline was pointing to. It's cooling down, but it is getting bigger and bigger. So its magnitude is very bright. Very easy to see. It's actually famous for a I think it's a planet that they've discovered around about it, an exoplanet. So that's why it's being studied quite intensely at the moment. Castor is Alpha Geminorum, and it is slightly less bright at about 1.55, 1.6. And it's a large blue star. But those are the two. Have a look for them. They're very easy to see naked eye, easy to see binoculars. And I'm going to look at the third brightest star in the constellation, called Alhena, if I'm pronouncing that properly. And Alhena is the foot of Pollux, of the brother or friend. It is, now that's an interesting star, this one. I can't quite remember its brightness, but it's third bright in the constellation, and it is in what's called the subgiant phase. It's not quite gone to red giant. It's spluttering. It's burning up all its fuel, and it's starting to die out. So it's starting to get big. It'll go red. So again, very important star. It's an important star when you're trying to find other things in the constellation, because you tend to bear off it when you're looking for other objects in it. And you can't look at the constellation Gemini without starting to look for some of the deep sky objects, and these two are particularly spectacular, and I would really encourage you to have a look for these. I want to look for the Messier object M35 and an NGC star cluster NGC 2158, and you can see that these are located at the tip of the toe of Castor, right off Castor. It's actually quite easy to find. You can come down the body and the leg of Castor and just find his toe, or you can find Alhena, which is probably the easiest one. I tend to then bear diagonally up through this bright star Mu, and you'll find it. Easy to find. You can find M35 with binoculars. It's wonderful. So there you go. In fact, right there it is. There's M35. It looks like a fuzzy patch. You will easily see the fuzzy patch in binoculars. A small telescope with as wide field as you can get. That says what you want. It's a beautiful, beautiful cluster. And this is a M35 open cluster. Now, this looks a bit dense. This is probably a slightly longer exposure astrophotograph. But when you look at it through binoculars or a small scope, it is beautiful. It's trails of curved stars, curved little jewels in the black velvet sky. It's just wonderful. And these star colors are, in this particular photograph I found on the internet, these are pretty close to what you would see. Really wonderful. And just off M35, which is quite a big object to look at, you find this denser denser open cluster, NGC 2158, and that is beautiful. It looks like a smudge in a small telescope, but if you get access to a bigger scope, you'll start to see A lot more stars in it. Really do try and find this. It's wonderful. It's one of those. It's one of the first Messier objects that I think it was Martin de Vries and possibly Anthony that encouraged me to find this. It's just it's wonderful, and it's beautiful. And if you like smooth curves and lines like I do, you'll enjoy it. The other deep sky object is something again that you can't go without. Is NGC 2392, also called the Eskimo or Clown Face Nebula. This is a planetary nebula. Again, it's a star that's reached the end of its life cycle and it's used up its elements, and it's basically imploded and exploded on itself, and it's created this planetary nebula. Now, this image I found today, and it's actually pretty representative of what you would see through a small telescope. You might not see the color. It might look more a gray smudge rather than this slightly faint turquoise, but this is pretty much what you'll see through a small medium telescope. Again, worth finding. It's quite a hunt. You have to do a bit of star hopping to find it, but it's definitely worth finding. And this, of course, is one of the famous Hubble scopes, where you actually see the dwarf star in the middle and all its tendrils and structures. It's just it's a beautiful sight. When people take astrophotographs, we don't get it as good as Hubble, but you can get something approximating it. You can certainly see some of the structure in amateur astrophotographs. So again, if we get clear skies, which I'm hoping for February and March, it's worth trying to take a picture. It's a detailed picture of it. Now, this is what I call an extreme challenge for the month. There is a comet in the region called Comet C2019 L3 Atlas, and it is in the vicinity all through February. It actually reached perihelion, I think, was at the end of last month, but it's still there, and it's holding its magnitude about +10, so it's not naked eye. Doubtful if it's binoculars. It might be big binoculars, but you'd certainly see it through a scope if you know where to look. So you have to aim for this reasonably mid-bright star, Mibsuta, in Castor, and the 1st of February. So right now it is located here, and it follows this path over the 28 days of February. So there are plenty of markers. There's plenty of good stars. It should be findable if the observing conditions are right. And something I am wondering is if I have, or if people have enough wide field telescope or camera or telephoto lens, could you get M35 and the comet in the same field of view? So that is what I'm calling the extreme challenge for February. So try and have a go at that. This is the star map for this month. And as you can see, the Gemini, not just Gemini, all the big constellations, all the big winter ones are all absolutely ideally placed for observing this month. There's Gemini there. The moon will be passing pretty much through it. So there's plenty of photo opportunities for crescent moons and constellation. So I think that's also worth a go. Here is the actual moon phase map for the month. Tonight we have a completely new moon, so it's absolutely jet black out there, and if there was no clouds it would be perfect, but I think at the moment there are clouds, so kind of stuffed at the moment. But there's your moon calendar. And a challenge I do want to set people, because I think this is very achievable. This was in BBC Sky at Night magazine in 2020 by the well-known astrophotographer and observer Pete Lawrence. But I also watched the British Astronomical Association monthly meeting webcast the other night, and they are encouraging us to look for the clair-obscur effects on the moon. They're quite wonderful things. They're optical illusions. They're revealed when the light and the shadow combine to form sort of recognizable patterns that our human brain seems to interpret as certain things. There are many of them visible on the moon. They are, as I say, a play of shadow and light, and they appear as something familiar on the eyepiece, and I'll show you some of those. You'll possibly have heard, I've almost guaranteed to have heard of the lunar X, which most people try and have a go at. The lunar V is another one. But most of the objects that require a specific timing, you've got to know which day and hour that they're at their best on the moon. Some of them do last for quite a time, but most of them last for a few hours. They're not instant, they're not like an eclipse, they're not like Rona chasing the eclipse down in Antarctic. They do last for a reasonable time. So you've got usually 2 or 3 hours to try and observe them with just the eyepiece, or you can try and take a photo record of them. And these are 7 of the most well-known clair-obscur effects, and they're dotted all around the moon. But I'm going to concentrate on these 4 here, which you'll see in my next slides. So this one is one I definitely want to. I hadn't heard of it before, would you believe? And I want to hunt this one down because I think it's wonderful. It's called The Face, and I have no idea how you pronounce this. Albertigneus. And the face is this shadow in the right-hand side of the crater here. The shadow is cast by the ridge of the top of the crater. And can you see the profile of the face? There's the brow, the eye socket, the nose, the lips, and the chin. So that's what you're trying to capture, either at the eyepiece or on a photograph. And that face is, where is it now? It's here. Okay, so it's about day 6.5 into the moon phase. So there's a challenge and a half for everyone and me. The X in the moon, or Werner X, that's well known. I have managed to do this a few times. It occurs just before day 7, but it's very, very distinct feature. It really does stand out. It's actually due to the lighting of the rims of three craters, but it does look like an X. And again, if you get a clear sky just at the right time, you will easily spot this. The V, I've also captured the V before. Again, it's pretty much the same time. If you catch the X, you'll catch the V as well. The V actually happens just slightly before the X, but it's only very slightly, to 15-20 minutes. The secret for doing these, just to let you know, is actually to set up your observing or photographic equipment in advance of when it's going to happen. So then you can watch the Terminator creep across, and your features, your X and your Y and your face will just appear. So there's your lunar V there as well. So you can see the lunar X is there. So they're on the same, pretty much the same part of the Terminator. And the last one I want to hunt for, and this is quite good. I've seen this one before through a scope, and it does look like a pair of eyes or specks, and it's the eyes of Clavius in that big crater down here, and very distinct. When you do see it, it really does looks a bit spooky, a bit odd. And it happens a couple of days later. It's about day 8.5. So again, if we get our scopes on it, get a couple of cameras up the eyepiece and just see what we can get. But you don't need cameras to see this. I just saw Anthony's made a question, what, no lunar octopus? Oh well, I'm going to please you in a minute, Anthony. Now, going to the planets, Jupiter is still just visible in the evening sky. I saw it a few nights ago, just for a short while. It's only about 10 degrees above the horizon at 6 o'clock in the evening now. So it's starting to get harder and harder to see. It's starting to dip, so it won't be with us much longer. Saturn, as Pauline said last month, in a couple of days' time, it will have moved behind the sun in the superior conjunction. It will vanish. It's effectively vanished. But it will reappear in the morning sky in mid-March. Now, if you're an early bird in the morning, it's worth getting up for. I mean, it's 7 o'clock, so it's not too late now. It's actually quite a nice time, but you will see an extremely bright Venus, magnitude minus 4.8. It is extremely bright. I've got it rises before the moon. I do mean the sun, of course. You'll see why I've got moon in my head, because we've got so many moon pictures for this month. But yeah, so minus 4.83, 7 a.m., 6:30, 7 a.m., really bright. It's stunning. And it does get reported as a UFO quite often, because people have never seen it before, and they're driving and they see it, and they report it into the police and Coast Guard and everything. Beautiful thin crescent. If you look at it through a telescope, you will clearly see the crescent. It's a wonderful, wonderful sight. Definitely worth going for. And Mars is there. You can see it down here. You will be extremely lucky to spot it. It's only 3 degrees above the horizon, and it's in the twilight. It's highly doubtful you'd see it, but Venus is the target for the month you want to have a look at. Now, Pauline gave an excellent presentation on the James Webb Space Telescope last month, and I've just updated it with the current news. There was a press conference last Friday where NASA, they described all the work so far to commission the observatory. And it's at its new home. It's at the Lagrange Point 2, which is about 1 million miles away. So it's actually got there. They have outlined the activation sequence for all the Webb's main instruments. So anybody that likes to look at a project plan, just go onto YouTube and you'll see the NASA on YouTube, and you'll get the report, and you'll get the project timeline. And there's a month-long mirror alignment. So the mirror is deployed, but it has to be aligned properly. And there's a lot of focusing work that needs to be done in order to achieve the resolution that Pauline and I were talking about there just a wee while ago. So that has got to be done. And that's all underway. And I am really, again, looking forward to some of the results, especially the early results that this space telescope is going to bring back to us. Now we're going on to the club news proper. Now I am obliged under Oscar regulations, that's the Scottish charity regulator, to notify you that our annual general meeting will be held via Zoom immediately prior to our monthly club meeting on Tuesday, the 5th of April 2022. You'll all be notified of this, you'll all get the link, and you'll all get the report and the accounts and any other documentation that will be prepared, and it will be distributed prior to the AGM for your perusal. And just bringing up at this point that all the office bearer positions are up for election: the chair, the secretary, and the treasurer. There are obviously certain people in place, and we have all stated that we're all willing to do it. But if anyone wishes to nominate someone else, or thinks they can bring someone else to the party, please let it be known, and we shall include you. Now, the HAST calendar, it's difficult to believe the first month of 2022 has already passed. It's already gone. And I want to, like Pauline did, thank everyone who bought one of these calendars. We have a very few left. I've taken an executive decision to, if you want one, it's only a £5 each, because it's only for 11 months now. And if you do want one, could you make it for collection or delivery? We got caught out in the postage. None of us obviously use the postal service as often as we ought to, and we got caught out because these are non-standard letters and they're fairly expensive to post. So we don't have very many left, but if you do want one, please just get in touch with us, and we will we'll get one to you somehow. Now observing, my goodness, this was so difficult last month. I mean, we all know what the weather was like. It was just terrible. We didn't get one single observing session at JSL Observatory. Even the reports, even people using their home observing, the reports of members were pretty thin on the ground. There were a few successes, and you'll see some of those in just a minute. We went up, the observing team, there was a few of us have been up there. We went up to inspect the observatory the last couple of weeks. We found that the water was off. That was a bit of concern. We thought there might be a great big leak or something. But Jerry went up to the NTS ops manager, and turned out they were carrying out maintenance. They just hadn't informed us. That's all sorted now, not a problem. The shed roof needs refelted, so we're going to organise that because we definitely need to do that. You'll be pleased to know that everything is still shipshape. There are no leaks, there's no dampness. The ventilation is good in the warm room, the office part of it. There's no mold, and all the equipment is in good order, good working order. So that is quite a relief, considering that for pretty much 2 years we haven't really used it that much. Another thing we tried, we don't have hardwired broadband at our observatory, but we tested a hotspot dongle-based alternative last week, and it was very successful. We were getting upload speeds of 24 megabits a second, and for those of you who don't know what that means, it means that's very fast. We should be able to webcast live from there. We're going to, I think, go up the coming week. Jerry, I'm sure Jerry's on, so Jerry, I'll give you a phone, and we're going to hopefully carry out some tests this coming week. If anyone wants to come up with us, anyone wants to maybe help test our YouTube webcasting, it would be most appreciated. Many hands make light work, and it's good fun doing some of this techie stuff. Regarding observing sessions, it looks more likely that notification of observing sessions is going to be more on an ad hoc and a last minute basis. Main reasons for that is that there definitely appears to be a change in the weather pattern. It certainly has been for the last while. It's just so many clouds, and we just can't guarantee getting a day or two at weekends anymore. We've also, although we've got some numbers in the observing team, we don't have a huge availability. So we need to be able to basically pick up the baton and observe when the skies are right and when we're available. So we will be using WhatsApp. It's going to be absolutely key to contacting members. So if you're not already a member of our WhatsApp group, especially Nebulous News, which is the prompter, please consider joining it. It's dead easy. Just get in touch with Lorraine, our membership secretary, and she'll get you hooked up to it. Dead easy, and it's good fun as well. Regarding our media, our YouTube channel is fully up to date. All our monthly meetings, including the most recent, including last month's, and today's hopefully will go on in the next couple of days. They are publicly available. Now that is a slight change to our usual operational plan. We normally delay making public our recorded meetings so that members get an advantage. However, we have taken the decision to keep it entirely up to date because I am giving a talk on a Zoom webinar to the British Astronomical Association on Wednesday, the 16th of February. And I want to use that also as an opportunity to promote our club UK and worldwide. And it makes sense to let the professional or very, very enthusiastic observers and people of influence, as I've called them, to see what we are getting up to right now. I don't want to see them, looking at something that's 3 months old. So this is a bit of a one-off, and I hope you guys are okay with it, but I just want to let them see what we're doing. And Pauline will, as I said, Pauline will email the contact details for attending the webinar. She'll probably do it in Stargazy Pie. I've just thought of that. And now your gallery of photographs, the most exciting part of the meeting, apart from the main talk, of course. So let's just get it all out of the way. Clouds. Fortunately, not all clouds are bad. We, for those of you who are on WhatsApp, you'll know we had an unofficial bragging rights competition live on our Nebulous News group a couple of weeks ago. And it was basically, if you can't beat them, join them. There were masses of photographs came in. We had a beautiful sunset up here. It was on the 12th of January. They were beautiful sunset clouds. They were a cloud formation called Altocumulus lenticularis. And they look like stacked plates on some of these flying saucers or whatever. This one was taken by Andy in Inverness, and the actual lenticular formation had broken up a little bit, but beautiful, beautiful colours. This was Dave in Inverness as well, and Anthony. Anthony at his work. I don't know whether he skipped off home early or not, but there you go. Some beautiful, beautiful colours contrasted against the lovely bright blue twilight sky. And this was my one in Conan Bridge. Now you can see the lenticular stacked plates formation of these clouds. And that's because Ben Wyvis is just a few miles to the left of this photograph, and the shearing wind comes off the mountain and shears the clouds and condenses them out to form these clouds. They were absolutely beautiful. They were stunning. This is looking northeast. And John Hansen, who also lives in Conan Bridge, John is probably looking a bit more westerly on this one, maybe northwesterly. And he's got the clouds as well. They were stunning. This is Lisa in Dingwall, and she caught them, and she caught you could see the vapor condensing out of the clouds, just dropping out and being lit by the setting sun. And Pat Escott, that's a wonderful photograph. Pat, I just love the colours in this one. Orange, red, just fantastic. Of course, sunsets are good, but sunrises can be even more spectacular. Matt got this beautiful one on the 17th. 17th was a wonderful day, because we got this wonderful sunrise, and then you're going to see all these beautiful moon pictures that we got in the evening. But look at the colours. I mean, that was spectacular. There's Lisa. Look at that. Isn't that wonderful? Oh, what a morning to want to get up. And there's Connor. Got these beautiful, beautiful orangey ones. And there's look at the structure, look at the waves as well in there. And of course, Dave, I mean, he's just picked up that wonderful, just on dawn moment where he gets that really deep blood red colour. Just, isn't that superb? But enough of clouds, enough. We have got issues with light pollution, and it's one of our remits. We work to try and minimise it, and work with the councils to try and sort it out. And we had an incident the other day. It was light pollution, and it was a flagrant breach of a Scottish Government planning decision and an appeal decision as well. And this was it. This is a chip shop in Muirvord who decided to blast a very powerful laser spotlight as an advertising beacon. Microsoft has stopped working. That's bothering me now. I may have to pause for a minute. If you just bear with me, it says Microsoft PowerPoint is restarting. Okay, I'm going to go down to this. I might not play the video clip again in case it was that kicked me out. But this was a very powerful laser they used as an advertising thing. They intend it to look like Batman in Gotham City. It doesn't work like that. It just creates a moving, diffuse light all over the sky, and you can see it for tens of miles away. This was the Scottish Government application and appeal outcomes. It very clearly says that the decision was issued, the appeal was dismissed and everything like that. I managed to go onto the Highland Council website and report this as a breach. So we don't tolerate this stuff. We don't take it lying down. If you do, it's the thin edge of the wedge, and we'll start to lose our night skies. I'm not sure. I know, Lisa, you reported it. Well, you reported it to me. You certainly made me aware of it, and I can't remember if you reported it. But anyway, this is the worst, one of the worst breaches I've ever seen. So hopefully something gets done about it. Now, there's sorry, so Lisa's just put in chat there that she actually officially reported it as well. So anyone that does, it just helps us. Now, some of us have been unpacking new equipment and doing a wee bit of observing and astrophotography. Anthony, now this is probably the reason for the clouds. I'm not blaming Anthony entirely, but Billy delivered his parcel, and Anthony kept beating us, and we could see it was going to be a tack scope, so we were all keen to see it, and he just released bit after bit by photograph. And he has bought this beautiful refractor telescope. It's lovely. And there it is, an F10 super corrected. So, I mean, it's just got no distortion at all. You can add extenders, you can make it very, very wide field, F16. It's lightweight, it can be carried anywhere. And what I actually do love is mentioned his super rustic modified AZ3 mount. Look at that. Isn't that an absolutely wonderful mount? That would look great in any star party. But the thing is, it actually works, and Anthony knows how to use it, and he has been using it big time. Now, a couple of months ago, I bought a refractor, and I haven't been able to use it in anger. So that was it set up out in my back the patio. That's a 90mm Stella Mira triplet from First Light Optics. Also out in the it makes the clouds look great. Okay, we've got to have a bunch of width in this place. So that's out there. What I also do, I can stick a digital SLR camera into the eyepiece slot. Doing 3D printing, you can make adapters so that you can get the right focal length, and I've got a 2.5 times teleview adapter just to magnify it up a bit. So all set up, ready to go. This is my equipment kit I take with me, and Anthony, I think, described it as the Star Trek Enterprise repair kit. It's not quite as good as that, but yeah, it does have a lot of kit in it right enough. And this is something that Anthony put me onto a couple of months back, and I'd never used them before, but these are variable polarizer filters. If any of you have ever had polarizing sunglasses, you know, something's used for, used to use them for fishing, especially to take the glare off the water. And if you got two pairs and you moved them against each other, you could block out all the light. You could polarize it so that you blocked out all the light, or you could let all the light through. And that's basically what it is. There's two filters, two polarizing lenses in there, or not even lenses, they're just glasses. And you can dial the light down. They are extremely reasonable priced. The 1.25 inch one is £19, and the 2-inch one is £30, and that is extremely reasonable for equipment such as this. I was keen to use it. I'd never used them, and I have used them, and you'll see the results in a short while. The moon is bright tonight, and we have quite a few pictures of the moon. There's Dave. Now he's put it on its side just to get it all in the frame. But isn't that wonderful? Dave is probably one of our best moon photographers. There's certainly never a month goes by without a picture of the moon from Dave. Lovely early crescent on the 6th. Lisa, I think, Lisa, this was your first go at it. Now, Lisa's also got a refractor telescope. I think it's a 60mm Williams Optics one. And I think that was the first time you'd put your DSLR into the eyepiece slot. 77mm, okay, that's fine. And you got a very, very acceptable crescent moon. And, you know, just about one day after Dave got his one. That's my one now that's without the polarizing filter. That's just straight into the eyepiece lens with a teleview. So that's why there's a bit more magnification than Lisa got, because I don't think, Lisa, you used a Barlow or a teleview, so that would be just straight down the tube. But very good picture. I'm very, very pleased with that. And I think everyone should be pleased with their pictures. Ross, wonderful. I like this. The moon, when it comes through just the edge of clouds, it often shows a corona. And you've got this. It's really hard to get the exposure right, because you're trying to get the corona and you overexpose the moon. But a little bit more, more attempts at that, and you will have that absolutely perfect. Great, great. And thanks for submitting that, Ross. That's exactly what we want to see. And Dave got, this is beautiful. I think this is wonderful. Dave's pretty much got this one right. You've got the right exposure of the moon. You can see the corona through these thin clouds there. I mean, Dave's an artist. Dave is actually an extremely good photographer, as well as an enthusiastic amateur astronomer as well. Really nice picture. Anthony, I think this is one of your, is it your first attempt? And this is a full moon on the 17th. And a full moon is so difficult to capture because it's glaringly bright. But you can see all the seas, you can see rays, you can see contrast, you can see the different mineral contents within the mares and the floors of the mares. This is just wonderful. Look at that around the edge. You can see some of the real edge craters. Be interesting to do a libration study on, Anthony. See what you can get over a period of months or even years. This is me. I use the polarizing filter now. This, I was really pleasantly surprised. You just dial it down and it just dims it. It stops any glare. Unlike using my dark green moon filter, which blots out the contrast, you can see big features like the Mare and bright things like Aristarchus there, but you don't see the detail of the feature. The polarizer just dimmed it down and allowed me to see all the different contrast. And what was really good about it was so easy to process. I processed it to deliberately bring out the bright features. I mean, you can see here, there's the Messier crater with the V trail in it and all kinds of things. There's the tips of the mountain ranges. I mean, you look at a full moon, or you take a photograph of a full moon, it is so difficult. I was able as well to look at the moon, take the camera away, and I was looking at it with a naked eye, getting the polarizer adjust so that it was comfortable. And what a detail I could see with the full moon. And as Anthony, I can't remember if he posted it in WhatsApp or whether he sent me an email, but he goes, you can forget about all that stuff that we say to people that, you can't observe the moon when it's full because it just washes itself out. Well, that's no longer true. So for, as I say, 20 quid's worth of polarizing filter, Anthony, thank you so much. I think that is a great addition to my toolkit. And I'm going to get great use out of that, both visual observing and some of my astrophotography. So as I say, thank you. And here are some wonderful pictures. There's Pat got a, like a 3/4 or more moon on the 21st of January there. Isn't that just wonderful? Perfect, really good image of a gibbous moon. You can see the Mare very clearly there. Anthony, there you go again. This is on the 22nd, so just a bit later. You almost did a phase study of the moon this month, considering it was pretty bad weather. The 23rd, so you can see how the Terminators moved across just even in that one day. 22nd to the 23rd. Dave, that would have been on the 26th, so not that long ago. I'm starting to go into a waning crescent. And these are arty ones. I like this. This is Andy Brough. This is wonderful. A bit of bud and sycamore, does it look like, in the foreground. On the full moon on the 17th. Dave, again, on the 17th. This is a good one, but this next one, I think is superb. That is a really arty picture. And somebody mentioned that Dave is creative. He certainly is. I think it's a wonderful picture. Just like it. Out of focus foreground and beautiful in focus moon. And this is good now. I'm scared to kind of wary about setting this going. I'm going to give it a go because I know that PowerPoint comes back again. But this was Patty down in and a pal down in central London. And just look at this area here, you'll see something quite interesting. Looks like the plane's going straight up. I'm sure it's not. I love that, Pat. Thank you very much for thank you for sending that. Now that was quite a lot of pictures of the moon. So now we're going to look at not the moon. And this was again on the 17th, so the night of the moon. And I just again I had the camera. I was just wanting to see what my refractor could do. And I took there's Albireo. That was quite early on in the evening. And I think you can see it's a double star, at the foot of the Cygnus or the Northern Cross, what you want to call it. And you can see quite clearly the difference in magnitude and colours of the two stars that make up Albireo. Here was one again early on. This is Jupiter, and it's 4 Galilean moons. So nothing spectacular. I just wanted to see what it could do. Just see what it saw. In fact, that was pretty low down, so that's probably why there's a bit of glare or murk around the planet. It's also hard to get the exposure right to get Jupiter and the moons together. Now, this is for Anthony. This was the Pleiades, again, just with the DSLR just in the end of the eyepiece. And this is clearly the Pleiades or M45 or Subaru. Now, Matt Lafferty, he drew on it an octopus schematic here, because Fritzi, one time when I was observing with her up at the observatory, she says, it looks like an octopus, and I could see what she was talking about. And I mentioned it to Matt, and he can now see it, so he drew it on there. But I put a thing, and people call it an octopus or a spider, or it could nowadays, of course, be a virus. So there's all different ways that the human sees patterns of things. So that was for you, Anthony, because I know how much you like it. The Octopusian people are winning. Okay, Fritzy. I hope we are. And Matt got Venus. I don't know whether you can see Venus. There's two lovely streetlights here, but Venus is down there on the horizon, just between the gable ends of these two roofs. So that's a nice picture, Matt. I like that. I do like that. And you can tell you were in focus because you've got these lovely diffraction spikes. Beautiful. We don't have a month goes by, even though without Aurora, even though it was cloud out most of the time. That was great, Lisa. It was nice to see that. And you know what? I didn't realize it, but you actually got the green. You actually got some bands there. And I know how that evening went. I mean, that was I think that was the inversion. You got temperature inversion. It just completely clouded. But well done, you. That was superb. And here's a really arty one. We see we're starting to get arty astrophotographers in the club. And you're going to have to tell me how you did this, because I do like this. You've got the Aurora. You can actually see there's a bit of purpley pink there as well. There's the Big Dipper on its side there, and the North Star. But yeah, you must be quite high up there, because that's there's a fair bit of snow there by the look of it. But yeah, good picture. And this is something that Lisa did. We were debating it, we're discussing it on WhatsApp, and it's a defocus star, definitely. And I think it's Sirius, but it could well be Procyon. But last year, I remember I did a series of exposures of a defocus Sirius, and got wonderful colour pattern and trail over a period of time. But look at all those colours, just refraction, just refracting the light, all the colours of the rainbow. I like that picture. I like it. I really do. Back in the start of January, I don't think this one was shown last month, so I just picked it out. But we got one quadranted meteor. So you're heading back into the quadranted. What would you call it again? The place where they start. My goodness, my mind's going. But it's a little double burster there. So there we go. Radiant, quadranted radiant. That's where the tail's going back to, just there. So that was the only meteor I got this month. All the rest of the month, it's just been awful, just clouded out. Mark Dre, now Mark's on tonight. Mark, thank you very much. Thank you very much for M42. That's great. It's great you have a go at these, and you can see the sort of bat-winged shape of there. You've actually got the core of that of the stars in there, the trapezium. Again, just slightly overexposed, so they blur into each other. But yeah, you've done really well there. I like that. This is something I was doing one night. I've got a mono astro camera, and I was taking S2 filter shots. I was planning and doing a whole night session with 3 different filters. Well, I got about, I was lucky to get 3/4 of an hour, but I got this shot. So this was done in an S2 filter, and you can see the structure. This is the M1 Crab Nebula, and you can see the structure this was picking out. Single frame. If I had gotten, 30 or 20 or 30 frames and stacked them together, that would be an extremely detailed structure of the Crab Nebula. I was hoping to get hydrogen beta and oxygen 3, but no chance. The cloud came in, and I've never had a clear night since. So I've got to work on that. I think that's a good project for me. I think that could end up being a wonderful image once I get all the data captured. But it's going to take a few weeks or even a couple of years to gather that data now. Anyway, that's just to show you what can be achieved, I think. And I'm finishing with this wonderful picture. And I'll tell you, I think it ties in pretty well with Pauline's talk tonight. Neil Weston of Aberdeen Astronomical Society got this dark nebula. Now, I'm not good enough to identify where it is. And I sent him a message on Facebook last night, but he's maybe not picked it up. But isn't that a wonderful picture? I just want to end there just to show what amateurs can do when they know what they're doing and they get the right skies to do it in. Anyway, guys, that's it from me. Thank you very much. And until next month, we'll see each other again. Thank you very much.
Thank you, Eric. That was superb. And yeah, that last photograph does tie in very well with my talk because, of course, they're the dark, dusty nebulae. So I don't know which one it is either, but it's lovely. And we'll almost have to search for Gemini in the sky. Nice and easy to find at this time of year. So no, that's a really good constellation to do. So thanks very much. And yeah, we'll just see everyone next month. Oh, and just to say thank you to everyone who's replied to the questions that we've sent. And if anyone who hasn't replied yet, if they can do so, that would be great to get a really good picture of what you all want for the direction of the club. That would be great. Okay, thanks very much, everyone.
Okay, I've just seen Gavin, this is Fritzi's Gavin is asking about Henrietta. Well, I don't think Henrietta is in there anymore. I'm hoping it stays like that. I'll have to go up and clean it sometime, the outside of it anyway, but I'm not going up at the moment. It's a bit dangerous. So anyway, no, it's not there.
Right, okay.
Cool. Right, guys, thank you very much for that. With that, I'm going to sign off. Clear skies and keep looking up.